Hello, this is Lab for magnetic braking. So to introduce this lab a little bit, the main purpose was just to use the interaction between a falling bar magnet and a tube of aluminum foil to study induced current and the subsequent forces that are generated from this induced currents, which are due to a change in magnetic flux, which is Faraday's law. The models we used were just a glow script coated model for our situation, which was the falling bar magnet and the aluminum foil. And the fundamental principles we used were magnetic flux and Faraday's law. And our main result was that the experiment displayed an induced current which created a force to oppose gravity and slow the falling of our bar magnet. And our coded model confirmed our experimental results. As for important physics concepts, the first one to understand is magnetic flux, which is basically a measure of how much magnetic field is coming through an area. So as you see, we have a surface integral which goes over a certain area, and it's basically doing the dot product just between the normal vector to the area and then the magnetic field. And once we have magnetic flux, we can see that Faraday's law states that an INF will be generated when we have a non-zero time derivative for magnetic flux. So when magnetic flux is changing over time, there will be an INF generated. Once we find this INF that's generated, we can find the current from Ohm's law by rearranging INF equals IR. Once we have a current that's induced, we can find the force on our object from the original magnetic field by putting in our newly found current and the original external magnetic field. We can also use this to find the force on the thing causing the magnetic field, since two things will have an equal and opposite reaction to one another. For our actual experiment, you can see our conditions. We have a system, which is a magnet that falls through a tinfoil tube. The tube's taped to a wall, and then I have a timer and a slow-mo video, which is used to track our times. And this is assuming that the tube is vertical and our magnet doesn't bounce around in there too much, and also the timing's perfect. And also there aren't magnetic interactions with any other nearby objects. As you can see, the time through the tube takes a lot longer than it does just to fall normally, and that's backed up by the times here for the tube drops being about 0.53 seconds and the normal just out in the air drop being about 0.29. So for the coded model, we basically just remade our real life scenario, but computationally. On the top left there, you can see those are the actual specs for the tinfoil tube I use. The first important function there is our function that generates the B fields on the rings of the tinfoil tube from the magnetic dipole, which is the magnet falling down. This is the B field that we'll use to generate our flux and our change in flux throughout the tube. That's actually our next important function there, which is going to calculate the change in flux like we do normally with the surface integral, and then we're going to take the time derivative of that so we can have our change in flux. And on the right there, you can actually see the full derived equation that we ended up with. Next, once we have this change in flux over time, we can rearrange Ohm's law so we can get the current generated. And then once we have this current, we can use it, like I said, to find the forces at play. So we can find the force on the ring first, and then we know that the force on the ring will be the same as the force on the magnet since they'll act on each other the same. And so that's what we're looking for. And so we finally end up with our force on the magnet, which we then can add up to the force of gravity on the magnet, and we can see what the final resulting force is, and then update the velocity and the position of the magnet from that. As for the results from our code, you can see we get a nice little image of the tube and then the magnet falling through, and then we also get a velocity versus time graph, which shows us that the velocity levels off, meaning our force from magnetic and our force from gravity actually will reach an equilibrium point where they'll be the same throughout the dropping in the tube. Also, you can see our real life results get pretty similar to our coded results with a time of 0.65 in the code versus like 0.53 seconds in real life. And this could easily be due to a difference in like the conductivity in real life not being quite up to what it should be due to other factors. So for some additional questions, if we were to decrease the resistivity in our tinfoil tube, that would mean with Ohm's law that our current would be able to be bigger, which would mean that the magnet would have a greater force on it and fall slower. Also, if holes were cut, there would be a breakup of some of our ring current, meaning that the current would probably be reduced a little bit and broken up some more. So it probably would fall a little bit faster.